Okay. Good evening. Okay, good evening. Are we all able to see the screen?
Good evening, sir.
Are you able to see the screen and get the audio?
Yes.
Yes.
Good evening.
Thank you. So we'll wait for a few seconds for people to join. I'm seeing people joining slowly. We are using the same link. And please note that these lectures or these tutorials are recorded. So feel free to access them, okay, via the channel. So I'll post these probably before the end of the day or as the
I
day.
think also the notes should be sent. The notes, lecture notes.
The lecture notes,
Are you able to share them on WhatsApp as well?
I think I can see how to do that. How best I can
Oh
do
yeah,
that.
sure. Very important.
We appreciate the data. Okay. All right. So I think that minute has elapsed and we can proceed, isn't it? There are too many calculations in this topic. So I urge everyone to pay critical attention and we need to move together. Okay. We can start now. So when we're looking at atomic structure, we are looking at atoms, or we are zooming into the structure of atoms. In this atomic structure, which we are going to discuss today, it is just the first part of the big thing, okay? The preliminary parts of this topic have been done in high school and so on, where you looked at protons, electrons, an atom has a nucleus, it has orbitals and so on. But in this tutorial, we are looking at, first of all, the nature of an atom, okay, or atomic structure in relation to the particulate nature of atoms, okay, and the waveform nature. So we're looking at atoms existing in waves and also existing as particles, and try to relate the two and see how are they connected. Okay, so atomic structure, we'll go straight into the waveform. We'll start with the wave nature of atoms. Okay, so wave nature of atoms obeys the general principles of waves, which gives us, of which we'll take c to be the speed of light, v to be the frequency, and that lambda for the wavelength in meters, not the SI units. There's meters for wavelength, there's seconds for cycles per second for frequency, and speed of light is in meters per second. So the waves will obey this equation of wavelength times frequency gives us speed of light. Okay. So this is our first equation. C is equal to wavelength times frequency. Then Max Planck assumed that energy is gained or lost in whole numbers. Okay, it is gained or lost in whole numbers. Where whole number multiples of the quantity HV simply means that HV is increasing by whole numbers. So this whole number will be assumed to be n, and n will be multiplying with this HV. Okay, so n will be either 1, 2, 3, and so on in whole numbers. okay, where h is Planck's constant, okay, which is that value 6.626 times 10 to the power negative 4 joules second, and v is the frequency, okay, of an electron or electromagnetic energy absorbed or emitted. So for this equation, remember that we already learned that we've already agreed that C is equal to wavelength times frequency. So if we make wavelength or frequency the subject of the formula in this equation and we replace it in Planck's equation, we can come up with another equation, or we can find ways and means to maneuver in case given a certain variable and not given the equation for it. Okay. So we look at an example. Emitted blue light of wavelength 450 nanometers by copper chloride. Okay. We have to estimate the increment in energy that is emitted at 450 nanometers by copper chloride. 450 times 10 to the power 2 nanometers. So the increment of energy or change in energy is equal to Planck's constant multiplied by V, the frequency. But what we have up there is the wavelength. So we need to calculate the frequency. That is why the first equation here, okay, okay, am I too fast, or are we at the same pace or page, on the same page?
You're too fast, sir.
So I slow down.
Yes, slow down.
Yes.
Okay, in case we
Yes.
don't finish, we only have 1 hour to squeeze this very big topic. So forgive me for pacing up a little, but I'll slow down for your sake. Okay, it's better we cover little than nothing, isn't it?
But yes, sir, we are not learning.
Sorry. Sorry, I can't get you. Your network is breaking.
You can just extend the time.
Just extend the time.
Yeah, just explain, sir. Since you don't have anything after the next,
Okay, let's see what we can do, and then we'll agree later on. Okay, so I'll start from the first slide. We said atoms exhibit wave nature and particulate nature. So wave nature obeys the laws of waves, or whatever laws govern waves, it obeys that. Then the particulate nature obeys particles. But these are fused together or come together and give us the duality nature of matter or atoms. Okay. So duality means there are two things in there. There's the wave nature and the particulate nature. So here we're looking at the wave nature, and we have our first equation, which is relating wavelength, frequency, and speed of light. Okay. So frequency V. Lambda is giving us wavelength, and C is the speed of light. SI units, cycles per second for frequency. Wavelength is in meters, and speed of light is in meters per second. So whenever given the speed of light in kilometers, convert it to meters per second. Or whenever I'm giving centimeters, always convert these values to their SI units. Then proceed with the calculation. Okay. So Max Planck came up with a theory, or he suggested that energy is gained or lost in whole numbers. Simply means a change of energy from one value to the next value is in whole number. There's a whole number constant multiplying. So this whole number constant, will take it to the n, and we'll say change in energy or gain or loss in energy is equal to n here multiplied by h, which is Planck's constant, and multiplied by v, which is the frequency. Okay. That is about Planck's equation. Now, relating what the two concepts that we've built, where we said C is equal to wavelength times frequency, and where we also said that change in energy is equal to Planck's constant, n times Planck's constant times frequency. We are going to answer this example we have here. So in this example, we've been told that blue light is being emitted at a wavelength of 450 nanometers by copper chloride. Okay. What is the increment in energy that is emitted at 4.50 times 10 to the power 2, or 450 nanometers by copper chloride? So here we've only been given wavelength, and we need to find the change in energy. And the formula for change in energy is change in energy is equal to h, Planck's constant, multiplied by v, which is the wavelength, or the frequency, sorry. So Planck's constant, we already know. We've been given, it's a constant. So we do not have the frequency. So we bring our formula, v is equal to, or c is equal to frequency times wavelength. We already have wavelength, we need frequency. C is a constant again. So changing the subject of the formula to v, which is the frequency, will be v is equal to c over wavelength. C is a constant in meters per second. Wavelength was given in nanometers, isn't it? So changing from nanometer to meter, okay, we will divide by, we'll multiply it by 10 to the power negative 9, isn't it? So this will give us 10 to the power negative 7. We'll change from nanometer to meter. We'll multiply that by 10 to the power negative 9. So our wavelength will now be 4.5 times 10 to the power negative 7 meters. So now multiplying this, dividing this C by the wavelength gives us a frequency of 6.66 times 10 to the power 14. Yes, sir, you can ask. I've seen you raise your hand.
In which instances are we using that formula which says energy, change in energy is equal to n HV? Because I can see you've ignored n in this formula.
Okay, so that was an assumption made by Planck. Okay, so he said that it increases in whole numbers. Are we getting that?
Yeah.
The changes in whole numbers. So here we just want to know the increment in energy, but we haven't been told of what was the initial, what was the next. Are you getting that? We do not have an initial value of this energy, okay? If we have been given an initial value, we have been told if n is equal to this much or has increased by 10 times, what is the energy change? So then we multiply that by 10.
Understand.
Okay, thank you. So therefore, our frequency is equal to 6.66 times 10 to the power 14 cycles per second. So we use this frequency and multiply with our h. Therefore, hv is equal to the frequency times Planck's constant. Finally, the change in energy will give us 4.41 times 10 to the power negative 19. So the sample of copper chloride with a wavelength of 450 nanometers will lose energy at increments of 4.41. So this will be the increment. We don't know what is the beginning and what is the end, but every time there's an increase, it will be by 4.41. Are we getting that, sir? The man who asked the question.
Yes, we are getting.
Okay. So just something to do with the formulas there. Change in energy is equal to Planck's constant times frequency which is equal to Planck's constant times the speed of light divided by the wavelength. So we could have gone straight to this formula or skipped to this formula and have found the change in energy. For those who have their, okay, yes, sir, you've raised your hand.
I'm actually a girl. So I wanted to ask about the previous, can you please go back to the previous page and then try to like explain more on the question.
Okay. So
first, you find the frequency.
Yes, you find the frequency. Because what we have here is wavelength only, and we do not know the frequency. Are you getting that?
I am. Yes, I am.
Okay. So since we want to know the wavelength or the frequency, sorry, we know the speed of light, which is c, the constant. So we go back to our first formula, which is saying that wavelength times frequency gives us the speed of light, right? So we make frequency the subject of the formula. And when we make frequency the subject of the formula, we will have this here. V is equal to C over wavelength, which is blending with our data given in the question. Okay, so once you find V, then you multiply with H, which is Planck's constant. Okay, so the other way, is to use this shortcut formula down here. But this one is just doing the same thing that we've done on the other side. This one is telling us that change in energy is equal to Planck's constant times frequency. There we found frequency first. Okay, but we can also say Planck's constant times C over wavelength, where C over wavelength is still the frequency. So it is still talking about the same thing, emphasizing the same thing. Okay.
Yes, sir. Thank you.
Thank you. All right. So atomic structure. So now an electron emits energy. Okay. As it is giving out energy, or as this photon, sorry, is giving out energy, we relate that energy, or change in energy, to what we've already done before in the previous slide. Okay. So where H is Planck's constant, V is the frequency of the radiation, and lambda is the wavelength of the radiation. Okay. So this slide here is emphasizing the sum of the two slides that we've already seen. Okay. So if this photon has a mass, okay, or we want to look at it in form of a mass, remember Einstein told us that E is equal to mc squared. Okay, and in that formula for Einstein, we make m the subject, which is the mass of the formula. It will be equal to energy over c squared. Okay, which is equal to, remember this E here is the energy. So when we get E up there and replace the hc over lambda where E is, we'll have the next equation here, which is hc over lambda over c squared, which when you simplify gives you h over lambda times c. So when you want to get the mass of a photon, you need to have Planck's constant, the wavelength, and the speed of light. Okay, that is how you can find the mass. This means that energy is quantized. It can occur in a discrete unit called a quanta. So this is the dual nature of light. So you can quantize. Sorry?
But also it's the school you open. Nachukua klasi nangu yonia number 2 dikonka.
Okay, so let's mind this the microphone. we accidentally turn it on, you might tell us a few secrets that we don't want to hear. All right, so here we're saying we're relating mass with energy. Einstein's equation says E is equal to mc squared. So in that E is equal to mc squared, we make m the subject, which is the mass. We want to know the mass of that photon, which is emitting that energy. Okay. So when we make m the subject, we'll say m is equal to E over c, and that energy, or the change in energy, which we already talked of earlier, is equal to Planck's constant times the speed of light divided by the wavelength. When we get this and substitute in Einstein's formula, it will give us Planck's constant over lambda times c. Okay. All right. So this is what we have: light as a wave phenomenon and light as a stream of photons. As a wave phenomenon, it will obey the laws of waves. As photons, it will obey the laws of particles, where we looked at the energy. So here we've related the two. Okay. So the first equation up there is just talking of the wave. The second equation here, we've introduced a mass. So now we are talking of a particle. Okay, it's a photon now. Initially, we're just talking of waves. Now we're talking of photons. We have added a mass. Okay, so the Broglies equation, the Broglies allows us to calculate the wavelength for a particle. So he's allowed us to unite waves and particles. Okay. So from our previous slides, where we simplified Einstein's formula, added the mass, we said that m is equal to Planck's constant divided by wavelength times speed of light. So for any particle with a velocity of v, okay, the corresponding expression would be mass is equal to Planck's constant divided by the wavelength times that velocity. Okay. So here at first we are looking at it as a photon, where we are using the speed of light. Now this particle, or this particle, has now been given its own velocity. We are no longer using the speed of light. So since it has its own velocity, we use v. H is equal to the wavelength times the velocity of that particle. Again, I'll repeat. Initially here we're using c, because we're using the photon. We are referring to a photon. A photon has the speed of light. Now here we are using a particle which has its own velocity. All right. So therefore, if we're looking for the wavelength of this particle, we'll say the wavelength is equal to Planck's constant divided by the mass times the velocity of that particle. Wavelength will be equal to Planck's constant here times the mass, or divided by the mass times velocity, or the product of mass and velocity. Okay, any questions this far? So this is the Broglies equation, where he allowed us to calculate for wavelength of the particle.
Yes, sir.
Yes, sir. Sorry?
The question. So wherever we are.
Sorry, sir, your network is, I don't know if it's my network or your network, but
Wherever we are using a mass, then V is considered to be velocity, not true.
Okay, sir, I can't get you. I think I'm not the only one. If someone got your question, they can ask on your behalf, but your network is not so stable.
Okay, I have a question.
Right, I was just wanted to find out.
Okay, kindly type the message. I think
So
if you
wherever
type,
we are using max, We use that V as velocity, not frequency.
Oh, sorry. Yes. So
Velocity.
in this case, we have already moved. Okay, so here we've moved away from, because frequency deals with waves. Are you getting it, sir? Frequency deals with waves. Okay, now we've moved from waves, we have come to particles. We are talking of this guy, de Broglie. Okay, de Broglie told us that we can calculate the wavelength for a particle. So we have moved from the waves, okay, to particles. So now we are dealing with a particle which has a mass. Okay, so this particle has a mass.
Thank you.
Yes, sorry. Has your question been answered? Okay, I see.
Continue, sir. Exactly,
Okay.
sir. You answered.
It's already answered. Next question. Yes, you've raised your hand. Please, you can go ahead and ask.
Yes, I wanted to ask, and the equation there, the on the screen, the third equation there, we have mass.
Yes.
Is equals to Planck's constant over wavelength times the velocity.
Yes.
Then here we have wavelength is equal. How is that related to the other equation? Because there we have mass, here we have the wavelength.
Okay, so what we've done is we've just made it change the subject of the formula. If you see, it's m is equal to h over wavelength times v. You cross multiply. Okay. If you cross multiply on one side of the equation, you're going to have m times wavelength times v is equal to h. Then you divide both sides by mv. Or you can try to change the subject on your.
I understand, sir.
Get it? Okay.
Yes.
Thank you. So we'll look at an example, then we'll answer some of the questions that I'm seeing in the message, in the messages. Okay. We'll look at an example, then we'll. Okay. So the atomic structure. Okay. Here we are seeing a line spectrum of hydrogen. So this one is showing us the energy levels as we are getting towards the nucleus and away from the nucleus. So the more energy you add to a particle, to an atom, okay, the electrons will gain more energy. So the electrons will have enough energy to overcome the force of the nucleus and will move away. So they will gain energy. So therefore, as you are coming towards the nucleus, you are losing energy. As you are going away from the nucleus, you're gaining energy. Okay. So this example we have here is the hydrogen atom, which has one proton and one electron. Okay. So electrons travel in circular orbits around the nucleus. The larger the orbits, the higher the energy. Okay. So energy is released as an electron falls from a higher energy level to a lower energy level. Remember, it has a lot of energy in the higher energy level. So as it comes to a lower energy level, it will release energy. Hence, the value will be a negative. As we do the calculations, you see the value to be negative. Okay. All right. So the most important equation comes from Bohr's model. The equation for energy levels in an atom is equal to, or E, which is energy, is equal to negative 2.178 times 10 to the power negative 18 joules. This is the constant, multiplied by Z squared over N squared. N is the number, okay? In whole numbers, N is in whole numbers, which is representing the energy level, okay? Or the orbital number. It can move from this, okay? So let's use energy level, not orbital number. So the energy level. Then Z is the nuclear charge, or the number of protons, or the atomic number, okay? Z is the atomic number, N is the energy level, okay? So the negative sign means the energy of an electron bound to a nucleus is lower than the energy of an electron further away from the nucleus. That's why there's a negative sign on that, meaning the energy, the closer to the nucleus, we have a lower energy. Away from the nucleus, we have a higher energy. Okay? So the more negative, if we have an electron very far away from the nucleus, where there's no interaction with energy, the electron has escaped this atom, it will have zero energy. It will no longer be bound to, it will no longer be bound to this atom. Okay. Okay, so the change in energy when an electron, okay, moves from energy level 6 to energy level 1. You want to calculate the change in energy from 6 to 1. So 6 is further away, 1 is closer to the nucleus. So the formula would be the change in energy, okay? Change in energy. So we calculate the energy first at level 6, and then we calculate the energy at level 1. The formula is, so here we're using the hydrogen atom. We're still using the hydrogen atom. The formula is given on the previous slide, okay? E is equal to negative 2.178 times 10 to the power negative 18 joules multiplied by atomic number squared over energy level squared. So here the energy level is 6, so we square that and we find negative 6.050 times.
Hello, sir.
Yes, sir.
Yeah, is negative 2.178 multiplied to negative 18 a constant or what?
It's a constant, sir.
What's the name of this constant?
It is sorry, I think I haven't stated it in the notes. Okay, so it should be both constant. I'm not sure if there's any other term for it.
Okay, sir.
Okay, if I remember the term, I'll let you know.
So sir, you use
Thank you, sir.
It's a
to
constant.
find the number of electrons.
Yes. Not the number of electrons. I'm not dealing with number of electrons. Remember, the N is telling us the atomic number.
Okay, so when do we use this formula? When finding
the energy. The energy an electron has gained or lost by moving from one energy level to the next energy level. Let's look at this page. Let's look at this slide here. So here we are saying that an electron is moving from the first energy level 1, which is closer to the nucleus. So we are imagining that our nucleus is down here. So from moving from this energy level 1 to energy level 2, an electron will gain energy. Moving from 2 to 3, it will gain just like that. So here we're trying to see the energy that an electron has lost for it to move from 6 to 1. Okay. We're calculating the change in energy of the electron. It had a lot of energy in level 6. Now, as it's come to level 1, it has lost energy. Okay.
Yes, sir. Thank you so much.
Okay, you're welcome. So, in order for us to get that, so we've calculated for both the 60th and the 7th and the 1st. So they are both negative values. Now remember, our formula is energy of the initial state minus energy So energy of the final state minus energy of the initial. Remember, final minus initial. Now the final state is a smaller value. The initial state is a larger value. And we are subtracting. So it is initial state, which is negative 2.178 times 10 to the power negative 80, minus negative 6.050 times 10 to the power negative 20. So this gives us a plus sign. So we'll add instead.
Excuse me.
Yes, madam.
I'm kindly asking where this one came from, the one on top, on the charge.
Where
is it?
Which charge now? The change in energy when an electron moves from energy level 6 to energy level 1.
Yeah, the second part.
The second part. For
yes,
n is equal to 1.
Yes.
For n is equal to 1 at energy level 1, the electron has more energy than for n is equal to 6. So which charge are we talking about now?
The Z. You say Z is for what?
The atomic
like
number.
Going back that,
The atomic
okay.
So we're looking at the hydrogen atom here.
Oh, okay.
Yes.
All right.
Z is the atomic number.
All right, sir.
Okay. So far, so good. We get the calculation. So what happens is that, okay. So the absolute value of E, here it's negative, okay? So for the, sorry, that's for the next calculation. But the change in energy here is negative 2.117 times 10 to the power negative 80.